Do you know that you can age a bit slowly? Do you know that you can change your weight? You can reduce your weight without doing any sorts of exercise. Well, the laws of physics allows that. And that simple law is based on one single action. This. If I take this ball and just let it go, it falls. But the question is, why?
What happens when an object falls? This simple question seemed to have perplexed scientists for many years. When you drop an object, we can't accurately tell that whether it falls with the same speed or it gains up speed as it falls. Now, these questions were first accurately and satisfactorily answered by this man, Italian astronomer, mathematician, and polymath Galileo Galilei. As the story goes, Galileo is said to have dropped objects from the Leaning Tower of Pisa in order to study free fall. His observations were quite simple. He said that as the object reaches the ground, it accelerates. Now, to measure the rate at which it accelerates, he came up with an ingenious experimental setup. It was a simple setup. It consisted of a long wooden ramp with a small angle of inclination, and a ball was allowed to roll down along it. What he observed was remarkable. Now, the attempt was to measure how much distance the ball traveled within a particular time interval, say 1 second. He saw that if the ball traveled 1 meter in 1 second, in the second interval the distance increased, and in the third interval it increased more and more. His calculations were, if the ball travels 1 meter in 1 second, it traveled 4 meters in 2 seconds, 9 meters in 3 seconds, and 16 meters in 4 seconds. Now we get a progression here. Let's find out the relation and the math behind this.
Well, from Galileo's experimental observations, we can find out, we can understand the mechanism and mathematics and the working of the free fall. So I'm writing the topic as Understanding Free Fall from Galileo's Observations. And for this, let's assume a ball which is at height h above the ground, and it is just allowed to fall freely on the ground. So here it reaches the ground, and according to Galileo, during a free fall, objects accelerate. That is, the velocity increases exponentially in respect to the time interval. Here it is the height, and this is the net displacement. And for this case, distance is equals to the displacement because the motion is in one direction. So if I represent it in a graph where velocity is a function of time, that is velocity time graph, we get a straight line passing through the origin. And if we calculate the slope of the graph, the slope of the graph gives us the acceleration of the ball. At height h, the velocity of the ball is 0, and as it reaches the ground, the moment it hits the ground, the velocity is acceleration multiplied by time. So here u is the initial velocity, v is the final velocity, a is the acceleration, and t is the time interval. Well, so at this point u equals 0, and on reaching t the value of v is, well, at. So if I name these points as a, b, c, it becomes a triangle, and this is the shaded region. So the principle is that if I calculate the area of this shaded portion, we get the displacement suffered by the ball from height h to the ground. So area of triangle ABC is just half multiplied by base multiplied by its height, and for this case the value of the base is the total time period, that is t, and the height is at. So we get half multiplied by t multiplied by at, so we get half at square, which is equals its height, that is its displacement. So this is our required derivation, and the relation between height, that is displacement, acceleration and time. Here acceleration is equals to the acceleration due to gravity, so which is represented by g. So that's all.
Well, from all these observations, we came to know how gravity affects speed of a falling object, its distance covered and time taken. But now what? What is this gravity? What is this physical phenomenon? And how it works? What causes the gravity? To get this answer, science had to wait for a few more years, until in the year 1665, when this guy, back then aged 23, came up with a beautiful explanation. English mathematician, physicist Sir Isaac Newton. Yes, I'm talking of the universal law of gravitation. The law had derived from empirical observations which Newton called inductive reasoning. In modern language, the law states that every point mass attracts every other point mass in the universe by a force acting along the line joining their centers. The force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Now, Newton's law of gravitation is said to be the first great unification of two independent theories. Number one, Johannes Kepler's laws of planetary motion, and Newton's classical mechanics. Well, to understand Newton's law of gravitation, at first we need to understand Kepler's laws of planetary motion. Johannes Kepler was a German mathematician and astronomer. His laws of planetary motion is among one of the best known works in the field of astronomy. Let's understand it.
Kepler's laws of planetary motion. Well, in my previous video I have explained in detail about all these three laws of planetary motion as well as the mathematical derivations. So for now I'm just writing the three laws. Well, the first law states that every planet revolves around the sun or the star in an elliptical orbit with the sun or star at any one of its foci. The second law states that the line joining the sun and the planet sweeps out equal areas in equal intervals of time. That is, the aerial velocity of the planet remains constant. The third law states that the square of time period of a planet is directly proportional to the cube of the distance between the sun and the planet.
Well, from Kepler's laws, we saw the mathematics behind the motion of planets. Now the thing we need to do is to derive Newton's law of gravitation from Kepler's laws of planetary motion and Newton's laws of motion. Now, here to derive the law of gravitation, we need Newton's third law of motion. It's known to all, right? Every action has its equal and opposite reaction. So let's derive it.
Well, now we have approached the final part of this video, where the thing we need to do is deriving Newton's law of gravitation from Kepler's laws of planetary motion. So the title goes like this: deriving law of gravitation from Kepler's laws of planetary motion and Newton's third law of motion. Let's assume the mass of a planet to be small m and the mass of the sun is capital M. The distance between the planet and the sun is r, and the angular velocity is represented by omega. Time period of revolution is t. Now omega is equals to 2 pi by t. This is our first equation. Well, as the planet revolves around the sun, a centripetal force is experienced by the planet. So the magnitude of this centripetal force F is equals to m multiplied by r multiplied by omega square, and just substituting the values from equation 1, we get the value to be 4 pi square mr by capital R square. This is our second equation. Now, according to Kepler's third law of planetary motion, the square of the time period is directly proportional to the cube of the distance between the planet and the sun. So t square is directly proportional to r cube, and t square is equals to k r cube, where k is the constant. From equation 2, F equals to 4 pi square mr by kr cube, and just separating the two terms, we get this as equation 3. Now 4 pi square by k is a constant value, since k is constant and it's getting divided by it. So 4 pi square by k is constant. Now we got three equations. The first one was of angular velocity, which is omega equals to 2 pi by t, and the second one was the centripetal force experienced by the planet, that is F equals to 4 pi square mr by r square, and the third one was F directly proportional to m by r square. Now, the centripetal force experienced by the planet is due to its revolution around the sun. Now here comes the idea, the main principle of this derivation, that is, when Newton's third law is essential. So according to Newton's third law, every action has its equal and opposite reaction. So since the planet experiences a force, that is centripetal force, the sun should also experience a kind of force according to Newton's third law of motion. Now from our previous results, 4 pi square by k is directly proportional to m, where m is the mass of the sun. So on removing the sign of proportion, we get g as the constant, and now we need to just substitute the values. from the second equation, where F is equals to 4 pi square mr by kr cube, we just separate the two terms, and this term here is substituted by the value of gm. So we get the formula gmm by r square. That's the final derivation, where G, capital G, is the universal gravitational constant. So this is Newton's law of universal gravitation and its mathematical derivation.
Well, now it's time for a short recap. Galileo showed us how falling objects accelerated. Kepler gave us the laws that explained the mathematics behind the motion of planets. And Newton came up with the universal law of gravitation. But there's something missing, very important. The question, what is gravity and how it is caused? Moreover, the magnitude of the force of gravity varies with latitude and height above the sea level. How much it varies, and what is gravity itself? What is its cause? Well, that's a topic for another Phygeek video. Stay tuned and remember, it's all about physics.